Okay, welcome to the final topic of Chapter 2. We're going to finish this today. This is you could sort of spot this one coming. This is where we're going to be finding the surface area of the non-prisms. The surface area of prisms was sort of straightforward because they usually were just non-curved spaces, non-triangular. So we got to be a bit more careful now. Of course, surface area, we're talking about adding up the area of all of the different faces of an object, which of course is quite tricky when some of them could be curved. So without any hesitation, let's get on with that. I think it probably is the trickiest. I mean, like anything in mathematics, you always have to be careful. And if you're careful, this should go fine too. But the questions can be quite involved, and you're trying to find things that are a little less obvious than in other sections. So you want to be quite cautious with how you approach this. Okay, so let's see what we got here. Now, this was already teased at last time when we were together. It's the volume of sphere is given, and we're also going to be talking about now the surface area of a sphere. Hard to measure with it being a rounded surface like that, but it certainly can be done. Right, so what are we looking at here? We've already seen that the volume is 4/3 pi r cubed, but now we're also noticing that the area is 4 times pi times the radius squared. Now, some of you may recognize that part of that formula, the pi r squared part, is familiar. That's the area of a circle. But if you want the sphere that is like the ball that surrounds that circle, it's just 4 times that. The proof of it is really quite fascinating, but we're not required that in our course, so I'll leave it to you to seek that out if you want help with that. But it is 4 times the area of a circle. Okay, here's a nice long problem I found with a different publisher. We're just going to go ahead and read this. Basically, there's a golf ball whose measurements are known, and we're going to start doing tons of different contrasts between it and the hole that normally we knock a golf ball in when we're successful. Let's see, we have a golf ball has a diameter of 3.4 centimeters. Find the volume of the golf ball. And this goes back to our topic last time, the volume of a sphere. Obviously that red ball in the upper corner is not a golf ball, but it's an appropriate sphere in order to sort of consider issues relating to spheres. First off, I noticed that the formula for the volume depends not upon the diameter but the radius, so I'm going to go ahead and divide that radius by 2 and put the number 1.7 there in that formula, 4/3 pi r cubed from your formula kit, and that leaves us with an answer of about 20.6 cubic centimeters. Now, you'll notice that I did not round this number off, and I'm always telling you, you cannot round numbers off and then reuse them in the problem. And I can see from reading the question on the previous screen that this number is going to come back again, so I want to take it as far as my calculator provides that number. Let's see what else say. Part B here. It says find the volume of the hole. Noting that the hole is related to the size of the golf ball itself. It says the diameter is 4 times that of the golf ball's diameter, and it's 3.8 times as deep. Right, so we need to make some comparisons here. I'm going to measure the cylinder, that is the golf hole, minus of course the pin or the flag that sticks out of it. If I take 4 times the previous diameter, the diameter is 3.4 centimeters, 4 times that is 13.6. Therefore, I conclude that the diameter of the golf hole is 13.6 centimeters. Therefore, its radius is half of that, or 6.8. I also know that they said that the golf hole was 3.8 times as deep. So I take the diameter of the golf ball and multiply by 3.4, and I get 3.8, and I get 12.92. Okay, I'm going to put those numbers on the side somewhere, and I'm going to work out the volume of the cylinder now. Now that's a prism, and that came also in our formula kit earlier in this chapter. Pi r squared height. Remember, pi r squared is the area of the base, which is the circular bottom, and height is the perpendicular distance. And I put my relevant numbers in there. The radius of the cylinder is 6.8, and the height is 12.92, and that gives me 1880, and that's a 3 significant figure accurate answer. So that's the volume of the hole. Now, I stored that information over here, so I didn't lose track of it. I'm not sure if that's going to come back or not. Find the surface area of the golf ball. Okay, so this is the amount of covering that's on its outside. 4 pi r squared, that's our recent formula. We know that the radius is 1.7. Pop it in there, and it's 6.16 square centimeters, and that's with 3SF accuracy. Now it says how many golf balls will fit in the hole. Well, here we go. we knew from a previous calculation that that's the volume of a golf ball. And if the golf hole is 1880, you just want to find out how many times 20.57953 fits into 1880, and that's division. So that means it's 91.4 golf balls. And for anybody who's golfed before knows that that's preposterous. There's no way that's going to work. So why is the calculation correct? Because we're just contrasting the two volumes. I mean, I suppose this doesn't account for the fact that if you stack a bunch of spheres, like golf balls, in that cylinder, there's a lot of wasted space, a lot of air around the golf ball. So, but if you were like to be able to melt them down or something, or just compare how the combined displacement of water, say for example, if you put golf balls in a big jug and then fill that water into the cup, they would actually measure at 91.4 golf balls, but it's not realistic overall. Okay, now let's see here. It's estimated that a particular golf course, 1 out of every 20,000 shots at a hole results in a hole in one. So how many people would have to play this in order to fill up? That's funny. So 1 out of 20,000, basically we need 91.4 of these things, and that's based on 20,000 shots resulting in a hole in one. So it would be, you multiply them and you get about 1.8 million golf shots it would take to fill up that hole. Okay, this is the other kind of surface area one that is a bit tricky. It involves a non-prism. So there's a taper to it, or a narrowing at one end of the shape. And this one has also got some rounded issues. Now, we're talking about a cone, a traffic cone. So here we go. A traffic cone is a height of 30, like a pylon or something that you would use in sports, like to, I don't know, run around, something like that. Traffic cone is a height of 30 centimeters from its base to its top. However, if you were to complete the cone, basically, it's been tapered or truncated at the top and sliced off 8 centimeters. That would have brought it to an absolute finite point. More on that in a second. The radius of the cone base is 6, and the radius of the top is 2.8. So it's a rather smallish cone, quite small. It says find the volume of the missing portion of the top of the cone, find the volume of the whole traffic cone, and now here it is. Find the surface area of the outside of the traffic cone. So what I'm going to do here is I'm going to take a look at a cone that would represent the traffic cone. And there it is there. Now, obviously, that black platform is not part of what we're doing here. So what I'm going to do is I'm going to remove that part and just consider on the conical part of the shape. So what we have is if you had an actually tapered cone that narrowed to a point at the top, you can see that the top part was sliced off in order to allow for the traffic cone, probably so they could stack appropriately or whatever. So if you're going to find the volume of the part that's missing that used to be there, we're going to have to consider some key dimensions here. Now, they told us that the top bit was 8 and the bottom bit was 30. They also told us some radius information, which I'm going to add to my diagram there. And now I'm going to just consider the formula. The volume of a cylinder is that, and the volume of a cylinder of a cone, is 1/3 that of a cylinder. Now I'm going to take a little shape here. 1/3. So this is the conical part at the top here, whose height is 8 and whose radius is 2.8, and that gives me a volume of 65.7. I'm going to store that information at the side somewhere. If I was to find the height of the overall cone, that would be the one that's sort of delineated in blue. I could then find the volume of the traffic cone part by taking the difference of the last two. So same formula, 1/3 pi r squared times the height. And in this case, the radius is 6, and the height is all the way up the side. That's the orange and the green arrows together. It's 38, leaving us with 456 pi cubic centimeters. Now, if you take those two numbers and subtract them, that's the large cone minus the top one that's missing, you're left with 1370, which is 3 significant figures accurate. Right. So now we're on to the hard bit, which is the surface area of the cone. To do this, I'm going to need to go back to my formula chart and work out that the area of the curved surface, the rounded part of a cone, is pi r L. It's not a 1, that's an L, where L is the slanted height, almost like the hypotenuse of a cone. How far that, like these blue lines along, obliquely going up the side of a cone here, that's the slant height. And very often we're going to be using a different form of geometry to come up with that length. And I'm just taking that look, and where did 8.48 come from? I didn't make it up. It's because you could see inside there with a comparison of the height down there to the radius, it is the hypotenuse of a triangle sitting right in there. So on the side, I worked out using the rule of Pythagoras that the slant height of that part of that missing part of the cone is 8.48 centimeters long. Now, if I then wanted to find the area of this part here, which represents the part that's missing, I follow the formula. Pi times radius times slant height, which is pi times 2.8, that's the radius, times this slant height, which is now revealed as 8.48, and I get 74.6 square centimeters. Now I'm going to put that number aside. Let's leave it there. And I'm going to represent the remaining part of the cone with a different diagram. Move that over to the side here. Now this is the whole one. And like before, I'll have to take a subtraction to find a key difference. I've added the slant height of 38.5. Again, where does that come from? Well, that's the entire height of 38 and the entire radius of 6. And it's like there's a Pythagorean right angle triangle sitting in there. So I got 38.5. If I use the formula for the area of a tapered cone, it's pi RL. L is the slant height. Put those numbers in there. And, oh, I made a mistake. I put 38, it's 38 and a half. Oh, well, we'll have to make an adjustment on that. And then we take the difference between those two. Of course, this number would change a little bit. And you have that. Now, we're off to the final section of this chapter. And it's section 2I. And they're going to be dealing with the volumes and areas of some oddly constructed shapes using our formula kit and our knowledge of 3D shapes. So there's the questions in there. They go 1 to 4. And I'm going to ask you to please do questions 1, 2, and 3. And that will bring chapter 2 to a close. And we will be having some Revision Village past exam question practice very soon. Okay, I'm here to help you. Good luck.